Hey, what's up, guys? Okay, so in this video that we are gonna to prove a very simple fact. It's very simple, but basically it's illustrating the main idea in the computer science or mathematics. There's a counting argument. So counting argument basically you just if we try to prove that something's very hard, then we just say that we just count the number of. Okay. So maybe it's a little bit hard to understand, but let's go in this simple example. I hope you guys subscribe to my channel. And this is theorem that due to Shannon, and I think it's very old, like maybe like 100 years ago that people already know. Okay, and this basically related to the circuit complexity. Okay, so all the study are Boolean function, right? So these are 0, 1 bit string, and bit string map to 0, 1. Okay, and so we have the elementary gate, right? So we have AND gate, an OR gate, or a NOT gate. Okay, so let's say, and so AND gate has two fan out and two fan in. So these are called fan. Okay, these are fan. And the NOTs have one fan out and one fan in. Okay. 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 And the problem basically is that I give you a function f. I give you f, and you want to ask what's the how many and or not gate that I can decompose that I can forms this circuit. Okay, so basically this is the circuit complexity. So basically one can just simply define that, which is the minimum number of n or not to compute f. Okay, for example, if I want to compute, yeah, for example, if I want to compute or all the OR gate, then if I want to compute all the OR gates, right? Basically, it's basically just x1 or x2 up to xn. Then I can just compute I can just use OR x1, x2, and then this OR x3 and keep going. So I guess there are like a minus one of them. Okay. So what this theorem tell me is the following. So what this theorem tell me is the what Shannon tell me that most of the function theorem. So most of the function or the Boolean function requires exponential circuit complex. Okay. So in quantum mechanics, there are several in quantum computing. There's a similar fact. Basically, one can show that most of the unitary, or most of the unit, oh, sorry, unitary requires exponential number of gates. So actually, these two proofs are very similar. So, but in this video, let's prove this one. So most of the function requires exponential circuit complexity. So meaning that if you give me a random function, there's a high probability that well, almost probability one that you need exponential n or not to form this function. Okay, so this is what counting. So we just count first we count how many number of functions that from 0, 1 to the n to 0, 1 to n. So this is simple, right? Because each we have 2 to the n, so each 2 to the n 2 to the n input can either have 0 or 1 output. So the number of function that one can compute is 2 to the 2 to the n. Okay. So in second, that suppose we have t gates, and then we can ask how many function that we can have. Okay. So we can cheat a little bit. So we can say that let's say x1, I have x1, xn, and also x1 bar up to xn bar. So I can do the negation, and also I can have constant input 0, 1, and I have t gate. Okay, so we can neglect not gate, right? Because all the not gate, then I can use this negation. So I can assume that I only have the n or gate. Okay. So the number of function that basically is the number of types. So the number of types of gate to the power t, right? Because each of t, each of the, let's say suppose I have t gate, right? So each of the gate, then I can choose the number of types. How many number of types? So in this case, that one can use two, then n or not. But basically, you can prove that any constant is the same. And the times the, let's say you give me per gate, then the possible input. And since we assume that there's two fan in or fan out, so I can choose, so there are at most two t. So two comes from the fan, the number of fan. Basically, it's because it's basically choose two, right? But that's it's just bounded by a square, and the t is the number of gates. Okay, because each of the gates, right? Each of the gates can choose two kind of inputs, and there are t of them. Okay, and what's the number of possible input per gate, right? So the number of possible input is a number of possible input is 2n, right? Plus 2. So 2n basically is x1 up to xn, x1 bar up to xn bar, and then this is the constant, right? 0, 1, or true or false, plus t minus 1. So t is basically because each gate, right, can take other's gate output as is in own input. Okay. So basically, it's 2 to the t, 2n plus t plus 1, 2t. Okay, and if you can like building up all the Boolean function, right? This should be equals to 2 to the 2 to the n. So it's it's trivial to see that t cannot be polynomial, right? If t is polynomial, then it is 2 to the polynomial. Okay, actually that means that's just let's solve this, right? So what we're gonna show is that 2n plus 2, 1 plus t, 2t, 2 to the 2 to n. Okay, so let's take it off, right? So it's t of 2 plus 2t log of 2n plus 1 plus t, 2n. Let's just take log. Base 2. Okay, so it's obviously said that if t is polynomial, then this cannot be true, right? Because if t is polynomial, then this is polynomial. A polynomial n, this is polynomial n, and this is polylog. But this is 2 to n, right? So t must be exponential. Okay, and actually you can get the precise bound by solving this question, equation, but I think it's not important. Okay, so this is a proof. And what one can actually use this proof to show that most of the unitary rays in the quantum computing, basically PQP, right, requires exponential number of gates. Okay, so this is similar proof, and then we will prove next videos.